So after that great start, I'll start my presentation. My name is Dhyey, and I'm an undergrad professor at NEPA Micros Lab. I've been working on the application of response-reformulated TDDFT to strong field dynamics on systems with double excitation character. Um, so I'd like to characterize the work I've been doing this semester as kind of a culmination of a few different things our group's been working on for the past few years. Mainly a continuation of uh, a former PhD student in our group, Davud Dar, now Dr. Dar. Um, so I'll first go over a little bit of the theory, then like the system that we chose and why we decided on that system, a few results I want to share, and then on to like what our future direction is before we get this paper out to the broader scientific community. So as we know currently, the cheapest way to propagate electron dynamics of a molecular system is using the time-dependent Cohen-Sham equations, which we can propagate for each of the Cohen-Sham orbitals. And so one thing, like we can imagine a case where this might fail, which is if we start driving our molecular system with a really strong field, and our system goes into a state that cannot be characterized as the ground, or it's in an excited state, and we start applying ground state functionals on there, we would start getting VXCs that are incorrect, and if we keep propagating, that air is going to start compounding, and we're going to get incorrect dynamics. And one case of that are gravity oscillations. So our group has found a workaround for this, which our RRTDDFT formalism. I'll just go over a brief derivation of how we got to the RRTDDFT equations. We start off with the full time-dependent Schrodinger equation, and we substitute in for the many-body time-dependent wave function. We substitute in equation 2, which is an expansion in terms of the energy eigenkets, which are the solution of the time-independent wave time-independent Schrodinger equation. And then we multiply both sides of equation once we've substituted in by psi m, which is the mth excited, which is the mth excited state, and we get equation 3, where V app is the fourth equation here. So if we just take some time and look at this term here, and we say that V app is a one-body operator, we can quickly see that we can get any VMN just using density functional theory, linear response, or quadratic response. So what we do is exactly that in this paper here. And the test case we use is the dipole moment, is evolving the dipole moment observable. And so that's also what I'm going to be kind of going over today. But this system, the work done here is using adiabatic parameters. So adiabatic couplings, adiabatic energies, and the system that I'll be looking at will have double excitation character. So the adiabatic approximation won't hold. So we'll need to use double excitation kernels, which our group has also developed. So we start off with the Casita matrix, and we define it using the traditional definition. And after applying a small matrix approximation and diagonalizing the system in a subspace of single and double excitations, where only one single excitation can couple with one double excitation. Because of the small matrix approximation, we get the following frequency kernels. The top one is discussed in the paper mentioned here, but this is actually a new one that we've discovered, and we fondly call DSMA Anya. It's actually a combination of DSMA 0 and DSMA A, which are mentioned in this paper. And so from these, we can get excitation energies, the electronic densities of the excited states, transition densities, and transition dipoles. We can't get state to state because we haven't found the quadratic response equivalent of this work yet. So now going on to the system that I'll be kind of studying. This is kind of going to give you a hint, but I'll first talk about some of like some of the sub goals we want to accomplish on the way of kind of getting these the electronic dynamics correct. We want to make sure we're getting accurate system observables such as excitation energies and dipole moments. We want to make sure they're good before we start propagating those observables. We want to make sure we're getting Rabi dynamics. We want to get Rabi dynamics between the ground state and the double excitation states. We want to get multi-state dynamics between like multiple states, because the paper that I mentioned initially on TDDFT only has 2-state dynamics. So we want to kind of broaden that up and include multiple states. And we want to get accurate electronic densities, which Anya will talk about in an hour-ish. And so the system that we ended up on was a harmonic oscillator with a softened Coulomb potential. There's also a slight anharmonic term, which I'll kind of go over in the next slide. The reason we chose this is because it's easy to diagonalize. We can tune states of opposite and same parity, which allows us to kind of get the levels in a favorable way to do dynamics. And the system is not simple, but it is simpler to understand, as we've seen. And so along the way, we've had 2 hiccups. We started off by just having just a pure harmonic oscillator with a softened Coulomb interaction. And the problem we have with this system is that when we diagonalize a Hamiltonian, we see that the ground state and the first singlet has the same difference as the first singlet and the third singlet. So, and so on and so forth. So the third singlet has the same difference as the fifth singlet and the fifth and the seventh. So when we start driving it at the ground to when we started driving it at the frequency between the ground and the first singlet, we start getting this unbounded growth, which is kind of problematic to describe with TDDFT because we would need like 15 million states. So we see here that adiabatic exact exchange is doing quite a good job at describing the dynamics, is one thing I wanted to point out, but the magnitudes are off, but qualitatively it gives a good description. So then we decided to kind of ruin this like leveling and make it kind of more jaggedy. And we added the anharmonic term and we made the lambda here 0.05. But the problem we get with this system is the excitation vector G, because of the small matrix approximation, turns into one number. And so when we sum G2 and G3, which are the excitation vectors for the new cone sham states that we've created, and we sum them, obviously DSMA sums to 1 because like that's the way we've defined it. But if we find the exact G2 and G3, they sum to 1.64, which means the small matrix approximation is breaking down. And that's because we have multiple single excitations coupling with one double excitation. And because the SMA restricts us to have one single excitation coupling with one double excitation. So finally, the system we ended up on is gamma equals to 0.05 and lambda is equal to 2. So we made the softened Coulomb potential even soft, like just a little bit softer. So now the results with this system. So I'll first talk about some of the observables we got. And yep, so as we can see, the excitation energies are great. Like there's great match. They only start getting kind of inaccurate at the 3rd decimal place. And the most important thing is that we've uncovered the 3rd state, which traditional DFT doesn't even have access to. We also get great dipole moments of the excited states, which Anya's been working on, and the reference to this paper is right here. And we also get the transition dipoles. Adiabatic exact exchange gives us one of the states, but again, we uncover that new transition dipole. So, and one last thing is the G squareds now are 1.09, which means our approximation is quite like accurate. It's holding well enough. So now the next step is to do the actual Rabi dynamics. And so the two states that we're going to choose are the lower line of the double excitation states and the ground state. So we're going to try to drive electron density between those two. And we do it using a plethora of methods. We're doing the exact evolution of the time-dependent Schrodinger equation. We're doing adiabatic exact exchange, real-time TDDFT. We're doing truncated TDCI. We're doing the DSMA parameters using RR-TDDFT, and we're using adiabatic exact exchange using RR-TDDFT, which is like we did in our previous work. And so we see that not only does DSMA give a better Rabi, like more accurate Rabi period, the density, the density, like if we look at the density at the half Rabi of each of the methods, we see that DSMA is closer matching to the exact. So yellow, here in yellow is the adiabatic exact exchange RR-TDDFT at the half density. And here in red, I mean, see, it's so hard to see. That's how accurate it is, basically. So if you can't see the color, it's not my fault. It's just how good it is. So we see that like they're basically just right on top of each other, which means that there's a good fit.
Sorry, what is on top here? The blue and
so
exact.
Yeah, so the exact is right there, and the truncated TDCI and the DSMA, they're just like all three are right on top.
The green dots there.
Yeah, the green dots are truncated TDCI.
And what else is on top?
And that's it. Exact
These
exchange,
these two, oh,
truncated, and then DSMA. So all three are right on top of each other.
Mhm.
Yep. And then so
Oh, yeah, of course.
and then on the purple, and then the purple is adiabatic exact exchange real time. So we just like there's just these fluctuations. So for that we just extracted the density at the exact half Rabi period because there's no Rabi oscillations here. So.
And your DSMA is also your time dependent, frequency dependent kernel used and the time propagation at that.
Yes. Yeah. And so yeah, we drove each of the methods at their resonant, their own resonant frequency. So something really interesting we noticed with this though is like I guess the next something like usually done is we would want to drive the system at the DSMA parameters at the exact frequency just to see what happens. And something interesting is that the DSMA actually gives these blobs here. And so like we were kind of confused on this, and just to kind of play around with the system, what we did is we replaced in the propagation code, we replaced the DSMA energy of the second singlet with the exact energy. And then we drove it at the exact frequency. And now we actually end up getting this Rabi oscillation. So there's something at play here that's causing some sort of like sensitivity in the system.
I would have thought it's the other way around.
What's right?
Would you have thought it's the other way around, that if you drive it on the exact frequencies, you don't get the oscillations, but whereas if you drive it on the DSMA, you get the
So here we're driving it at the DSMA's own frequency, and we're getting the Rabi oscillation.
yeah.
And then when we drive it at the exact, we get these blobs.
Yeah.
Did I misspeak?
I think you said it.
Oh yeah, sorry. My bad.
Okay,
Yeah, that is
good.
bad.
All right.
Yeah, sorry about that.
That's perfect.
Yeah. Yeah, so exactly when we replace when we replace in the propagation, when we replace the energy of the second singlet with the exact and then drive it at the exact, then it works.
And so I think you're saying that in the RRT sequences, right? You have the
I'll go back to them.
Yeah, sure. Just point to what you.
Yeah. So just to clarify, sorry. Fancy pronunciation. So here, like we're just propagating these two equations, right? So let's if we,
Yeah, and
yeah.
you're using the DSMA, like your derived frequency dependent kernel quantities for all the parameters that are going in,
Yeah.
right?
Yep.
And now what you do.
And then, yeah, so we just take EM, so for EM2, we'll put in the exact EM2. And then we drive the system at the exact frequency. If that's,
And then you get the.
and then we
routes.
get the Rabi oscillation. But if we have the DSMA E2 and we drive it at the exact, then we just get those blobs.
But then if you have the DSMA E2 and you drive it at the
DSMA, then it works, yeah. So the methods are self-consistent.
So
each
yeah,
other.
which it makes sense,
No.
except what was surprising is that our DSMA frequency and the exact frequency
Yes,
are
yeah.
remarkably close. I don't know why it's so sensitive. We sort of do the mathematical to move
Yeah.
this, and it's just very simple.
Yeah, just up to the third.
Yeah, that's.
That's how we do-
Point something maybe.
Yeah, and others, the Rabi dynamics, were like the one with Anya in the other paper, it wasn't so sensitive.
So,
This should be adiabatic energy difference.
No, it's the stressed frequency dependent kernel.
Ah,
Or excitation energies, right? That are like the
okay.
numbers
That
are,
one that goes in the kernel for
yeah, it goes, I mean, it's,
single to double.
yeah, and it's very accurate, right? And like, you know, if we didn't look at dynamics, we just look at excitation energies, right? We're like, this is a really good approximation. And I think it is, right? Except somehow this kind of driving dynamics with this charge transfer, or yeah, this charge transfer, slightly, not really charge transfer, but you know, a dipole change character is really sensitive, which we don't really understand why the system is, right?
It's like degeneracy, like it has to be perfectly,
Yeah,
like the energies have to be. matching.
Usually what happens if you're detuned Rabi, right, you know, you get a little bit off, right? So you
Yeah.
don't get 100% transfer, but not 0, but like this is basically
Oh,
there.
I see.
There's just like this on you.
Yeah, why it's so
that's
sensitive.
weird.
Maybe a bug in the code.
I don't think so, no, because we tried like the same kind of, yeah, we should just, we need to just analyze it a bit more.
Yeah.
figure out where
Bug
it's-
in my code.
No, because we tricked on Mathematica some things, so.
Yeah, so what we're doing right now is like in the last one of our sub goals, which is getting multi-state dynamics. So we're driving the system with a sine squared pulse, and we're just playing around with the parameters. And actually, one interesting thing we're seeing, it's not up here, but TDDFT like real time actually does quite a good job of replicating the exact dynamics in some cases, because the VXC term is the external potential is so high that the VXC potential is lowered, and in the limit it kind of like the propagation is correct. So that's one thing that's interesting. But this is actually a case where where we're seeing that real time is kind of failing. It's in the orange here, and the DSMA is kind of accurately following around with the exact. Yep. And this is using truncated TDCI, so we can see kind of the comparison between the how each coefficient is. So I forgot to put our sponsors and stuff here. But I'd like to thank everyone in my group, NSF, I guess, because they fund everyone. And then yeah. Yeah. Any questions?
So tell me something, are these double excitations, usually are they optically dark?
Optically dark as in, okay, yeah, I mean in DFT they would be, because
I mean, you know, it's an exact. Right, the double excitations, I mean, you know, are they dark excitations or are they bright?
dark excitations as in, sorry.
Well, if you like if they produce light or they couple to light.
In other words,
If the
the
transition is on zero.
Yes, so I mean in this case, I mean this isn't a real system, but I think in butadiene.
So, yeah, so sometimes it's thought that if it was a pure double excitation.
Yeah.
It would be dark in linear response because you need two photons. But those are rare. Most states have a mixed character, right? Like, so this one has a mixed single and double character, right?
Yeah.
And butadiene it also does, but in butadiene, the 2AG is dark for a different reason, and that's because of symmetry of the molecule. It's a 2AG is the same symmetry parity type rules, selection rules. So that's a different reason for the.
So in your 1D model then,
Yes,
is it a bright, it seems to be a non-dark
it's.
mode because you did everything is divocal.
I mean, it's. I would say. Again, right? Like it's a mixture between the two.
Yes, so this is what you said, Carsten, because so it's non-dark, and that's because that state is not a pure double. We should be saying states of double excitation character, but that's too long, so we should abbreviate.
Double excitation.
Yeah, so they're mixed single double excitations.
As
Because the electron drift.
Some must have something to do with the sensitivity.
The
sensitivity that we noticed to why how you drive it.
Well, I'm not so sure.
Maybe
You think?
it could be.
I guess
Just right. I mean, somehow I'm just trying to rationalize
See.
why you change it by less than 1%. Driving frequency,
Yeah.
you get this enormous sensitivity. Maybe it's
Yeah.
got something to do with the character, whether it's
Right. But what's also interesting is like there's a bunch of analytical stuff known about two-state Rabi oscillations, right? But and so, for example, even in saccharide, there's a formula for a detuned Rabi oscillation and coefficients, right? But the problem is that's relevant when the two states have the same dipole moment. Now, if we're looking at two states which have slightly different dipole moments, surprisingly, I haven't found an analytic formula for the detuned Rabi. For on Rabi, the coefficient evolution is known in terms of Bessel functions in series like this, right? This is BMTs.
yes, yeah, BMT.
But the detuned I haven't found, and I don't know I'm not sure, right? But I think, when you're off resonance, like how, because if this is for an analytic formula, we just read up, yes, I see, so it's very sensitive because the denominator is, you know what I mean? Like,
Yeah, I think
I don't have any analytic thing to feed off.
working on.
Yeah, no, we have to work it out.
I guess just to clarify, I think
Maybe you're
if like the I think the G values represent how much double excitation
Single.
character, like the single excitation character each have, and then so if you just do one minus that, that's a single function.
right. Except for the exact case in this case.
Yeah, I mean, yeah, this is
So then the two level.
Yeah. in the two.
Any more questions?
So that means we don't need non-adiabatic functionals anymore, right? We can all do RR TDDFT and that solves everything.
Yeah, well, although we don't need non-adiabatic functionals in the non-equilibrium, but we need non-adiabatic frequency depend, like we need it for the linear response. Sorry.
So we should patent that.
Yeah.
Okay, thank you guys for your time.
Great.